So let me show you that. It involves a bit of manipulation. It's all just algebra, but you have to combine things together, and it's kind of cool the way things work out numerically. So let me show you that. So in a separate tab, I've done another calculation for this problem. Here we have the moment of inertia expression that we've been working with. I've filled in now specifically oxygen, carbon, and sulfur as labels. I have sulfur 1 and sulfur 2 for the two masses. And here are the two equations and two unknowns shown symbolically. And so it's only the capital R's. There's an ROC and an RCS. They're the only two unknowns. Everything else we would have a number for. We could fill in a number for. I've taken the original equation and just rewritten it by getting rid of this fraction and multiplying through by the mass of the total. And that's how I generated these two equations. So if I identify some collections of constants here, like A1, A2, B1, B2, C1, C2, I can group together the pieces that are going to be coming out when we try to subtract these two equations. And so that's what we see down here, a little simplified version. So here are the two original equations, and here are the two simplified versions of that. All I've done is replaced these collections of constants with appropriate coefficients here. These A1, A2, B1, B2, C1, C2, they would just be numbers that could be evaluated. And here's where we're solving the two equations simultaneously, right? You subtract one equation from the other. So A1 minus A2, A1 minus A2 is, and then if we take the difference here, we get some things to cancel, and we can collect together the terms involving ROC and RCS. Here's where the cool thing is. If you take a look at what C1 and C2 values are, they're very close to one another. They would only be different in the case of the masses of the isotopolog. And so these numerically would be very close to one another. In fact, I've got them right here in the spreadsheet. Here's the values of C1 and C2. They're essentially the same all the way out to the 9th decimal place. So that means that we can just drop this term out. And if we do so, we'll have an equation that we can solve for ROC. And here we see what ROC is equal to in terms of A1, A2, B1, and B2. So that's now a known result because we know these numbers. Having solved for ROC, then we have to go back to either of these two equations, plug it in, and we have a quadratic equation for RCS. And we'd have to use the quadratic formula, which I'm showing here. Here are the numbers as they would play out in this problem. Again, I've converted from hertz, that's given in the homework problem, to AMUs times picometers squared. And here are the masses again, and here are the values of the various collections of constants that I've labeled as A1, A2, B1, B2, C1, C2. And there's A1 minus A2 and B1 minus B2. And so this would then, once you plug in those numbers, give you the same results that solver would, but it would be by solving the algebra rather than just numerically solving for the equation through solver. Hope that helps. I want you to try this out. Try to put it into Excel. You can use either the solver method or the algebra method, but try to get a result so that you can finish up that homework problem and submit your answers here. And by verifying that you can do this particular homework problem, you'll know that you have at least one of the exam questions pretty well in hand when we get to that part. So thanks very much for listening, and I'll see you again.